Hey, welcome back to Microsoft Connect. Today we're going to talk about building planet-scale apps, and we're going to feature real-time personalization and Azure Cosmos DB in this session. My name is Andrew Liu. I'm a PM on the Azure Cosmos DB team. And basically the way this session is going to go is we're going to first talk about the business and technical challenges of one of our real-world customers, ASOS.com. We're going to talk about how you can build real-time personalization architectures. And then we're going to do a very deep technical dive onto the data tier, in which we're going to talk about Azure Cosmos DB, the resource model, the system topology, partitioning, global distribution, and consistency. Also, at the very bottom of this feed, there is an area where you can submit your questions. Please do feel to submit your questions. I'd be happy to answer them at the end of this session. So to start us off, let's take a look at some of the business and technical challenges faced by some of our real Azure customers like ASOS.
ASOS wants to be the #1 fashion destination for 20-somethings around the world. Fashion is in our DNA. We have just over 12 million active customers, over 800 brands, and introducing about 4,000 to 5,000 new products onto the site every single week. We don't have shops. People know about ASOS from the internet. We have 1 minute when our digital platform is out. We're not serving our customers. We want to be there for our customers 24/7, 365 days of the year.
When you have 85,000 products in your product range, it's vital to have a personalized consumer experience. We took a couple of big decisions early. The first was to go microservice, and the second was to go Azure Platform as a Service. We're using advanced machine learning techniques to synthesize custom and product characteristics, to create data sets that will allow us to rank products' relevance in milliseconds. And what that will mean for our customers is we're going to show products they might like, those will be more relevant, the experience will be more relevant. And clearly, this is all about maximizing the sales from the time the consumer shops with us. We're using Cosmos DB because it allows us to distribute the data models to be near the services wherever in the world they're deployed. We like the immediate elasticity. We like very low latency for random reads. And Azure has delivered as a rock-solid platform to create an ever more compelling consumer experience.
Awesome. So give you a quick recap of that. So ASOS is a global company. They're a fashion e-retailer, and they're delivering to customers around 200 countries around the world, right? And so what this does is it translates to a technical requirement where now you need globally distributed infrastructure in order to serve that international customer base. On top of this, they're getting tons of traffic. They have millions or tens of millions of active customers. That translates to hundreds of millions of different page views each day. And this is growing at a 25% year-over-year growth. And on top of all of this, this huge scale workload, basically they have another set of technical requirements in making sure that the website that they have running is rock solid, highly available, and this way, basically, when you're dealing with something like Black Friday or Cyber Monday, the last thing you want to see is an outage. If you see your website go down, that is customers walking away and shopping somewhere else. On top of this, you want to be able to deliver very predictable performance. This is in terms of both throughput and storage. And from a throughput scenario, basically, you need something that elastically scales out to handle these heavy seasonal bursts. And from a latency perspective, basically, this is to help you provide those very, very snappy web experiences so that your page doesn't take forever to load. And then on top of this, when you're a fast-moving company like ASOS, you don't want to spend your time babysitting servers, messing around with data center configurations, messing around with operating system updates, database software updates. Instead, what you want to do is you want to focus on building your application and delivering and maximizing your impact and your value for your product and business. So let's take a look a deeper look at one of the many services that ASOS is running within Azure. And basically, one of which is the real-time recommendations piece. Real-time recommendations is a really interesting scenario because of how latency sensitive it is. Basically, when you, as a shopper, come onto the ASOS.com, the product details page, what you want to see is a tailored experience. If you see this, you might also like box in your product details page, and none of those products make sense to you, then as a user, this is just noise. This is just advertisement, and you're tuning this out. However, if this becomes increasingly relevant to you, so if you find that you like to shop for a certain category of products and that the website really understands who you are and tailors that experience for you and things that you really love, then as a shopper, you're going to engage. You're going to go, hey, that looks cool. I want that, right? But the thing is that when you load these kind of experiences onto a website, these need to load very, very fast. In other words, they need to be able to identify who this user is, know everything about the user, know how this translates to product recommendations, and immediately serve these recommendations back in millisecond time. In order to facilitate this, let's talk about how one such architecture and how you can build this kind of experience. Basically, what we have here is an example of the Lambda architecture. Lambda architecture is this concept of having a hot path and a cold path. And on the cold path, this is where all your clickstream data is going to go. In the example here, we're using Event Hub into Azure Data Lake Storage. And this is because this clickstream data doesn't actually need to be served with high concurrency or with low latency. Instead, what we want is just to hold a very, very large volume of data and then do data analytics on top of this. To facilitate the analytics and building the machine learning model, what we've used is Spark ML. Deployed on Azure HD Insight. And what it's going to do is it's going to take all of this clickstream telemetry and it's going to build two sets of models. One is a bunch of featurized vectors for each individual product. The other is a featurized set of vectors for each individual user. And if you take the dot product of the user vector with the product vector, now you have the probability of what is the probability that that user is interested or will buy that product. And if you now are able to calculate this for each individual product, then you can very easily facilitate recommending what the shopper should see. Now, in order to do real-time recommendations, this is going to be a little bit more challenging than your traditional things like email marketing. For email marketing, really, it's not latency sensitive. This analytical job can take days to run. It can take weeks to run. That's fine. However, users are not going to go to your website and wait days or weeks for your page to load. They want to see a page load up within under a second, and that means for each of the individual components, you're looking at millisecond latency time. So what we do is we take all of those materialized data models and we're going to use Azure Data Factory to push them up into Azure Cosmos DB. And Cosmos DB is going to give you that very, very high concurrency, low latency capability. It's going to be able to do random access reads off of the user profiles, the products, in under 10 milliseconds. And what you're going to do is as user comes into the product details page, it's going to go hit your decision engine. In this case, we're hosting the decision engine on Service Fabric because it's easily scalable and it's highly reliable. It's going to make a very, very low latency query to Cosmos DB to understand who this user is. It's going to do the computation on what is the recommendation, and then it's going to immediately spit back out onto the product details page. Now, this is a very high-level view of the world, and for the rest of this session, what we're going to do is we're going to do a very deep technical dive on Azure Cosmos DB because this is one of our relatively new services that is not as well understood, and what I want to do here is demystify that and teach you how you can build these highly scalable, highly performant workloads on this distributed database. Now, from an Azure Cosmos DB standpoint, for those of you who have not seen this, I'll give you the quick TLDR pitch, right? And basically how I view this service, I like to view it in terms of this layering a cake model. Basically, at the very, very core of what Azure Cosmos DB is a globally distributed, massively scalable database. And basically, it does three things very, very well. It's going to be partitioning, replication, and query/index. These are the core ingredients of Cosmos DB. In turn, by focusing really, really hard on these three pillars, we're able to build really nice, new, novel capabilities like turnkey global distribution and leverage the fact that Azure is available in 30, 40 different regions around the world. What you can do is you can easily replicate that data and bring it closer to where the users are at the click of a button. On top of this, the partitioning allows you to elastically scale out both storage and throughput. So whether you are starting small with a gigabyte and you want to grow out to a petabyte, or you want to start from just a few requests per second and grow to millions or tens of millions of requests per second, we give you that elasticity through our server-side partitioning model. Backed by this, I mean, this is a service built by performance. We're hardcore performance geeks, and we really, really care about latency. And to the point where if you look at all of the other database vendors out there, they're typically, when they talk about performance, they talk about, hey, here's the average latency, or here's the best case latency. However, no one's actually talking about the P99 latency. And what the P99 latency is, if I take all of these requests, rather than looking at the best case scenario or the guy in the middle, we're going to actually look at the worst case scenarios. And we're going to guarantee and financially put a backed SLA so that 99% of these requests are all delivered with very, very low latency. In order to deliver this low latency promise and combined with replication, the thing that really makes global distribution work is the tunable consistency model. A lot of databases force you into these hard extremes of strong versus eventual consistency, and what we do is we give you a tunable model so that you can make the right trade-offs for your application. And finally, for this service, it's a fully managed service backed by comprehensive SLAs. It's highly available. This is made possible by a highly redundant architecture. We'll talk a little about this in just a second. But basically, what this translates to is a guarantee, a financially backed guarantee of 4 nines of availability and 5 nines for multi-region reads. On top of this, it's still the only cloud service today that offers SLAs around latency, throughput, and consistency. Now, on top of this core underlying infrastructure, this platform, basically what we can do is we can project natively and very efficiently several different data models. These data models are the key value, column family, document, and graph data models. And these are surfaced through a variety of different APIs, including a document DB SQL API. New today with Connect, we have announced the Cassandra API. And then, of course, we have a Gremlin Graph Traversal API, a Tables API, and a MongoDB API. So now let's dive into Cosmos DB, and we're going to start from a high level, and we're going to go increasingly deeper and deeper down down the rabbit hole. The very, very first thing that you'll want to understand is the resource model, because at the end of the day, when you connect to Cosmos DB, this is actually what you're interacting with. Specifically, what you're going to do is first you're going to provision a Cosmos DB account, and this is basically the URI and key so that the application knows what to connect to. To provision an account, it's super easy. What you do is you go to the Azure portal, you click on New, Databases, Azure Cosmos DB, and then you give that Cosmos DB a name. This is going to be your URI endpoint. After this, you're going to choose which of the APIs you want to interact with. You're going to choose which Azure subscription to host this under. You're going to place it under a resource group. And then you're going to choose what is the starting region. Don't worry too much about the starting region because this is a globally distributed database, you can always replicate to additional regions as well as remove older regions. Now, once you've created the account, basically it's a 5-minute click create and it's there. You're not spending a week, configuring VMs, installing software, setting up replica configurations, data center configurations. Screw all of that. In 5 minutes, you are ready to go. And the next step you're going to do is you're going to create a database. And the key thing that I want you to remember here is database is a logical abstraction. At this point, we actually still have not provisioned the very, very first piece of hardware that's going to run the database engine. Instead, that's going to be way further down in the tree. But basically, the database is going to be a logical grouping of containers and users and permissions. The users and permissions are the objects that you can use to do fine-grained access control, where a permission is basically a tuple of a user and either a container or something underneath it. Now, containers are where things actually get interesting, and I call this container because depending on which API you're accessing Cosmos DB through, it's going to look a little different. For example, if you're using any of our document-oriented data models, then this container is going to be called a collection, whereas if you're accessing through the Tables API, it's a table, and if you're accessing one of our Graph APIs, this is a graph. Underneath this container, we're going to have the records, But before we get into that, let's talk a little bit more about the containers. Here I have a screenshot of me adding a collection through one of our document-oriented APIs. And basically, all you need to do is you give the collection a name, basically an identifier. And this is going to be actually really interesting. You're going to set the throughput on the container level. And because you set the throughput on the container level, containers are actually the first time you're actually going to start getting into physical infrastructure. Basically, the throughput's going to dictate how big of a cluster we're going to initially provision. And basically, you can make this as small as you want, as large as you want. Think of this in terms of requests per second. And from here, we can also dynamically grow or shrink that container. You can actually scale this on demand. The secret sauce, or really not the secret sauce, but one of the key things that makes this all possible is the concept of a partition key. In order for us to actually distribute all of your data across a large cluster of machines, as well as route requests to the right node within that cluster, what we need to know is a hint from you on how you want things to be distributed. This takes form in the form of a partition key, and we'll talk a little bit more on partitioning here in just a second. Once you've provisioned a container, you're ready to actually store your individual items. These are going to be your actual data, right? Your records. If this is the document-oriented model, these are your documents. If it's graphs, it's going to be vertices or edges. And if it's tables, these are going to be the table rows. On top of this, we also have a few other resources depending on the API you're accessing. We have this concept of store procedures and triggers, and uniquely to distributed databases, we actually support multi-record transactions. These take form in the server-side programmability API of store procedures and triggers. And then, of course, the user-defined functions gives you ability to greatly augment the query language. Finally, we have this concept of conflicts. Now, 99.999, infinity 9% of the time, you don't need to worry about conflicts, but they still exist, and you should still know what they are. Basically, because we're a globally distributed database, and we take care of things like automatic failover. When a natural disaster happens, we'll automatically move your workload from region to region. Basically, what we're doing is, as you write data into the database, we're replicating it all around the world. Now, what were to happen if you were to write data to one region of the world and then something disastrous happens? Let's say a major earthquake or a hurricane starts disrupting network connectivity for that region of the world. Well, what ends up happening is some of that data has not actually replicated. But the thing about Cosmos DB is we believe data loss is a cardinal sin. In fact, some of these databases out there, what they do is they buffer writes in memory, and they acknowledge right away. We don't play these kind of tricks. We think that is evil. Instead, what we do is, when you write a record into the database, what we do is we actually durably commit that to a quorum of replicas in that local region and before acknowledging that. And that all happens in less than 15 milliseconds. From there, replication to other regions is going to be asynchronous. And if there are any data that has not been replicated during an automatic failover, we'll make sure that we keep durability and surface them in the form of conflicts. The reason why we need to surface them through conflicts is if you fail over from an application perspective, just because you're not talking to another region, you still want access to the data that should have been replicated. So you might, as an application developer, write that data again into another region, let's say region number 2, but when region 1 comes back online, basically you now have 2 copies of the same data, and one might even have moved forward in time with repeated updates. And so in order to merge this conflict, you're going to now need to have your business logic on defining, well, does the first write win? Does the last write win? Do you want to have more complicated merge logic? And by surfacing this conflicts feed, we guarantee the durability of your data and make sure that you're able to actually keep it and handle this. Now, the resource model is kind of the surface level view of what you're interacting with. Let's also talk about what is happening behind the scenes. And the way I view this behind the scenes, basically starting from the globe, we have planet Earth, right? And planet Earth, basically today we have deployed about somewhere between like 30 and 40 Azure regions, and each of these regions are actually going to be comprised of actual physical data centers. Just because you're using the cloud doesn't mean that there isn't an actual machine or computer actually running the actual workload. And so we host these in data centers all around the world, and within that data center, we set up all of these racks that we call stamps. These stamps are then broken up into fault domains, and these fault domains basically mean that anything within the fault domain has a shared set of infrastructure. So things like a network switch. And what we do is we actually deploy these massive clusters of hundreds of machines across tens of different fault domains. And within that, we're going to actually host the actual database replicas. The reason why we do this is so that way we can spread replicas across many different fault domains, and this is why we're actually able to offer you an always-on database. Basically, if a network switch goes out, if a disk fails, don't worry, we actually replicate all data across 4 replicas per data center, and the moment a replica goes down, we'll bootstrap another replica. On top of that, updates will be rolled out in a controlled fashion on a replica at a time, and so that means no matter a hardware failure or operating system update, this does not actually surface itself to you. Basically, it happens all transparently. The database just remains available. And the replica becomes a core building block for your containers. Basically, the replica is our database software. It has our database engine. It has a query layer, the index layer, as well as a resource manager for doing the resource governance, giving you predictable performance, as well as all of the the resource governor for doing that, as well as the transport layer for doing all of this global distribution and replication work. So, given you have an idea of how our underlying infrastructure looks, let's actually dive into partitioning. And as I mentioned, a container is where you provision throughput and storage, and what happens is we can elastically grow that as much as you want. Basically, we can give you as many replicas and partitions underneath that as you want. You basically tell us, and we manage the partitions for you. And the way we actually make this happen, I mentioned, is the partition key, right? And choosing the right partition key is actually the #1 design decision you're ever going to make in Cosmos DB. So if you only take one thing away from this talk, learn about partition keys. This is a very, very key thing in Cosmos DB design. And the way the partition key works is it's a logical partitioning abstraction. Keep in mind, a partition key is not a physical partition. It's a logical abstraction. And basically what we do is we will take that partition key and we'll hash that and break that into a huge range of possible values. In this example, we're going to use user ID because we might have an application that scales the requests as well as the storage over time by the number of users. It routes the requests by user. It basically queries by user, as well as it does transactions by users. And when we look at behind the scenes, the physical layer, basically the first thing we do is we hash that value. So that way, if you have, let's say, a bunch of sequential IDs going from 0, 1, 2, 3, 4, 5, you're not actually forcing everything into a single partition and waiting for that to fill up before moving on to the next. The hash will give us a nice pseudo-random distribution of values, and this will range from 0 to max value. Now, from 0 to max value, what we'll do is we'll actually divide that range of values into a set of partitions. So let's say, for sake of example, you have a workload that requires 4 partitions to serve the storage needs and 2 partitions to serve the throughput needs. In that case, by provisioning 4 partitions, we're actually able to guarantee you that there's neither a bottleneck on storage or throughput, yet we've still provisioned the minimal amount of hardware to keep the costs controllable and down. And in this example, since we have, let's say, 4 partitions, what we'll do is we'll actually break the range of hashable values or hashed values into 4 quarters. And the first quarter is going to map to partition 1. The next quarter is going to map to partition 2, and so on. Basically, now what that means is that we're actually co-locating partition keys on the same physical partition. Now, what happens when a partition needs to grow? Just because we've co-located partition keys on the same physical partition doesn't mean you're actually going to run into issues. Basically, this actually gives us a very, very clever technique in which we can simply split that one partition range and say, you know what, this range of values, 75 to 100, this is starting to fill up. It's 80% full, and so what we need to do is we need to get another partition. So what we do is we'll split that and turn that into 2 partitions. So, values 75 to 87 might go to one partition, 88 to 100 might go to another partition. And that way, for that same partition range, you now have double the throughput capacity, double the storage capacity. And this is actually happening all behind the scenes. You don't even need to lift a finger. Basically, the database will grow, or rather your container will grow as your application grows. It'll do this while simultaneously maintaining high availability. Sorry for the typo on the slide. And basically, this is the under-the-scenes look of Cosmos DB. And I love this because as a developer, what you care about is how many requests per second do you have? How much storage do you have? You don't really actually care about the node math, the number of partitions. I mean, in some sense, there is initially kind of this ego thing where you go, wow, take pride, you're running on a large number of nodes. But over time, this just becomes a headache. And what you really care about is what that translates to you, and that's storage and throughput. Now, let's talk about the best practices for choosing a good partition key now that you understand how this works behind the scenes. You basically have two high-level design goals. Number one, what you want to do is you want to distribute the overall request volume as well as your storage across as many partition keys as possible. What you want to do is you want to avoid hot partition keys. And let me give you an explanation on why that is. So an example of a bad partition key would be current time for a write-heavy workload. If you choose current time as your partition key and you have a write-heavy workload, that means at any given time, all of the requests coming in have the exact same current time value, the same partition key value. So all of those requests are going to go to the exact same partition, meaning that one partition is going to run super hot. Meanwhile, all of these other partitions are just left idling, doing nothing. That's not how you scale a workload. Instead, what you want to do is you want to load balance and distribute both the storage and the request volume across as many partition keys as possible so that you're distributing this workload on the underlying physical nodes. On top of this, what you want to do is you also want to choose a partition key such that it makes your queries very efficient and that you can run multi-record transactions using the out-of-box store procedures and triggers. And basically, this is going to steer you towards an opposite end of the spectrum. If you want to hit design goal really, really well, I mean, basically, this is going to steer you towards very, very fine-grained partition key values, maybe something like the ID, while on the other end, in order to make queries really easy, make transactions really easy, you might actually choose a very, very coarse partition key. And this is because think about what's going to happen. If you partition a system by, let's say, the user ID, and you run a query that looks something like select star from this collection where user ID equals Andrew, then basically what the SDK can do is it'll parse the query. It'll go, you're querying by the partition key is Andrew, and therefore what I'm going to do is I'm going to hash that. I find that the hashed value is 123, and I know that 123 is going to map to partition 5 because I know all of the ranges and the partitions. And so I just efficiently talk to partition 5, and that gives me back a response. Now, if I run another query that doesn't have the partition key, let's say it's select star from this collection where birth date equals October 20th. Well, the thing is that you might have records across any number of these partitions that has relevant data, right? Like users, you might have many users that have birthday October 20th. You might have no users that have birthday October 20th. So what the SDK needs to do is now it needs to ask every single partition and go, hey, do you have the relevant data? It'll use the index on each one of these underlying partitions. Now, what's going to happen next is, regardless of how much data you have, if you have no data, no relevant data, basically you're only going to have like one RU. So the occasional fanout's not too bad, but there still is going to be a real throughput cost. From a latency perspective, we can actually highly parallelize each of these fan-out requests. And because they happen in parallel, the hit on latency is actually minimal. However, from a throughput standpoint, if you have the occasional fan-out, okay, that's fine. But if you have 100,000 requests per second and all of them are doing fan-out, then now you're no longer scaling because every request translates to a request on every partition. So what you want to do is you want to define a partition key where you can intelligently route these queries, at least for the bulk of your query workload. Basically, this is now going to give you a set of steps on how you want to actually think about your problem. The very, very first thing you want to do is you want to ballpark the scale needs in terms of size and throughput. And all you need to do is get a rough order of magnitude estimate. It doesn't matter if it's 1,000,001 versus 1,000,002, but it does matter if you're talking about 100 requests per second versus million requests per second. And the reason why I say that is because at the end of the day, if you have only 10 gigabytes of data and like 1,000 requests per second, honestly, you can fan out every request, because at the end of the day, you have like a single partition running your entire workload. Who cares about fan out? Fan out's the exact same thing as non-fan out. However, if you have a petabyte of data and tens of millions of requests per second, well, you probably have a very, very large number of partitions underneath this container, and therefore fan out's going to be a lot more costly. So that's step number one. Step number two, you're going to understand the workload, and specifically, you're going to break things down into a read path and a write path. For the read path, what you're going to want to do is you're going to look at the top 3 queries or top 5 queries, and you're going to look at the where clause. In that where clause, you're going to identify common filters, and if you see the same property being queried over and over and over again across different queries, basically you now have a very good list of candidates for what a good partition key might be. For writes, what you're going to want to do is you want to understand the transactional needs, and basically a store procedure or a multi-record transaction is going to be scoped to a single partition key value, so you do want to take that account. And on top of that, because you're already doing this exercise, you also want to understand the ratio of insert requests versus update requests. Insert versus update actually has more to do with the object model and less to do with the partitioning, but you still want to think about that because it does have an impact on your design. Basically, if you have, let's say, a large unbounded array, and you have lots and lots of update requests that basically append to this array and grow this array, basically over time, these update requests are going to get more and more costly. If you change these update requests to updating a gigantic record with all of the array elements, and instead make that just a single insert, so basically you co-locate array elements not in a document, but in separate documents in the same collection, you can drastically reduce the RU cost of these write requests. Now, it's going to be very, very difficult to actually optimize for 100% of requests. So what you want to do is you want to operate off of Pareto principle. Use the 80-20 rule. And what you want to do is you want to optimize for the 80%. So if the 20% is less than optimal, fine. However, if you optimize for the 20% at the cost of the 80%, well, at least from my point of view, I might be questioning, why did you do that? Is that the right design? As one more general tip, don't be afraid of having too many partition keys. Lots of people come to me and say, hey man, I am, let's say, partitioning by ID because I have a key value access pattern, and I just want to distribute this as evenly as possible. But the thing is that I have millions of IDs, and so therefore, am I going to have too many partitions? Is this going to get really costly? No. Partition keys are a logical abstraction. We actually co-locate those partition keys using consistent hashing across a frugal number of underlying partition sets. And because we do that, you do not need to be afraid of having too many partition keys. If anything, the more partition keys you have, the more scalability your application has. Because if at the end of the day you only have 10 partition key values, then at most we can grow this to 10 underlying partitions. However, if we have millions and millions of partition key values, then today we can start small with like maybe 1, 2 partitions and grow that to millions and millions of partitions to really, really scale that workload. Now, partitioning is only one aspect of the distributed system. The other is replication. And Cosmos DB is actually kind of unique in that not only is it good at replication within a region or doing DR into another region, but because it has a tunable consistency model, it's actually very, very good at doing global distribution. So let me talk to you a little bit about why global distribution. Number one is the obvious one. It's high availability, right? If you have your data and your database replicated to multiple regions around the world, then basically you have resiliency against things, any kind of disaster, whether that be a natural disaster or a geopolitical disaster. Basically, now your application is resilient to a region of the world going dark. On top of this, we actually put a multi-homing API. What that means is that all of the different database regions are actually using the exact same URI. And using the multi-homing API, what that translates to is if you have to do an application, a database failover, an automatic failover or a manual failover, you don't have to redeploy the application. Because it's the same exact URI, it's going to automatically start redirecting all the requests to the next, or to the correct region. But here's the kicker. It's not just for high availability. It's actually for low latency access all around the world. And basically, packets, when you replicate data from one part of the world to another part of the world, basically, no one has solved how to actually send information faster than the speed of light. At least, if you figure this out, I mean, you deserve a Nobel Prize. But just because we can't ship packets faster than the speed of light, we can still cheat the speed of light. The way we cheat the speed of light is we exploit data locality and bring data closer to where the user is. People have known to do this for decades using content delivery networks, but the thing about CDNs is they use edge caching, and it's only good for static content. It's not very good for doing heavy write workloads or when you want to do queries over structured content. So this is where Cosmos DB is one of the, in a unique position. We have solved this for dynamic content. Basically, we can now give you very, very low latency access by shipping data closer to the user. And so when they are ready to query, they only route requests to something very, very close to them and get very, very low end-to-end latency times. In fact, this is why for real-time personalization, Cosmos DB is a golden standard in terms of database. Now, the way global distribution works, here I've opened up the Azure portal. I've gone to the database blade for one of my Cosmos DB accounts. This is actually a screenshot. And what I've done is I've clicked the Replicate Data Globally button on the left-hand navigation. What you'll see is immediately a map with little dots all around the world, and each of these dots basically represents an Azure region. In order to add a region, let's say today I have an application in my database deployed in central US, and my application is really taking off. I am now seeing usage in Europe. I want to replicate to let's say, Western Europe. All I have to do is click a button, and then and that's it. That's actually how you set up global distribution, and that's why we call it turnkey global distribution. It's really like just turning a key and things are just on. You can click any number of regions of your choice. You can do 10 region deployments, 20 region deployments. All you do is you click what regions you want, you hit that save button at the top, and now your database is configured and it'll start live replication to all of these other database regions. Here I have just a simple illustration where I have a Cosmos DB account. I have an application using the document DB API. It's deployed in West Europe. At least the application initially is deployed in West Europe. And let's say, for sake of example, my database is located in Southeast Asia. If it's in Southeast Asia, now we have the speed of light problem. And if you look here, when I run my test workload, basically I'm seeing 180 millisecond latency. This is unacceptable. If I want to do, let's say, real-time bidding or real-time fraud detection or real-time personalization, this is a deal breaker. Think just if you have to do now multiple round trips to the database, oh my goodness, that application is going to be slow. So what we do is we do global distribution. We bring the data closer to the user and therefore the application. Basically, users around the world will connect to a set of application instances deployed around the world hidden behind a traffic manager. That traffic manager is going to route them to the closest application instance, and that application instance is going to talk to a Cosmos DB endpoint closest to it. And now suddenly you're seeing single-digit millisecond latency. Here in my test workload, I'm seeing 4 or 5 millisecond latency. And honestly, we actually have, I mentioned predictable performance earlier. What we do is we actually guarantee at P99 for a typical record, a 1 kilobyte record. If you do a point lookup on that record, you're going to see less than 10 millisecond latency at P99. You're going to see less than 15 milliseconds for write operations at P99. This thing is blazing fast. Now, once you've set up your globally distributed database, how do you take advantage of automatic failover? Well, if you go into the Azure portal, the first thing you're going to do is you're going to turn this switch from off to on. And this enables automatic failover. The current model for Cosmos DB is writes are affinitized to a single region, reads are made ubiquitous to all regions. We do have some design documents for doing multi-write region. Feel free to look up our white paper, as well as we will actually be supporting this with new out-of-box features down the road in our roadmap. Now, given today's model of single write region, now you want to actually control from an automatic failover standpoint. If, let's say, central US were to get knocked offline, what region will now serve my writes? We have a simple drag and drop interface. You can reorder these secondary regions. So for example, in this setup, I currently have Southeast Asia as my next designated write region in the case that Central US were to go down. And if Southeast Asia were to go down, then North Europe would be promoted as the next one in line. If I want to switch it, I simply drag and drop, and I click the Save button at the bottom of this pane. In addition to setting a global policy for failover, you can also override that at the application instance level. So rather than taking the default global order of regions I want to connect to, let's say you have a bunch of application instances deployed in in the US and the Asia and Europe. And basically, you don't want all of these following the global order, right? The global order might say connect to Central US, and it makes zero sense for a Southeast Asia application instance to then connect to Central US. Instead, it wants to talk to what's closest to it. And in fact, it might even want to fail over in a different priority. If I now add another region, let's say Korea or Japan or India or any of the other any of the other Azure regions in that world, I might want to choose that as my backup region. Similarly, for the US application instance, it might want to fail over to something close to it as opposed to something really, really far away. So the way this works is here I have some sample code where I'm instantiating the document client for the document DB SDK, and as part of that, I have to give it a connection policy. Rather than giving it the default connection policy, what I'm doing is I'm configuring it, and underneath the connection policy, I actually have this array, an ordered list of preferred locations, and basically I'm telling it what are the regions I would prefer this particular instance to connect to. In a real-world scenario, rather than hard-coding these values into the application code, what you'll want to do is make this app config driven and or environment variable driven. Basically, all of these location names are just string enums, and you can have this all driven by the app config. In addition to automatic failover, you can do manual failover. The way you do manual failover is you click on manual failover in the Azure portal, and this is useful for two reasons. Number one, you can use this to actually test failover, do business continuity, disaster recovery drills. But on top of this, let's say tomorrow that you're finding, well, all of my write requests were actually coming in from Central US before. Now I'm seeing that North Europe is actually getting where the bulk of write requests. What I can actually do is change which is the preferred write region using this manual failover function. In fact, you can even go so far as to build a follow the sun model so that if you have a workload that is typically hot from the hours of 9 to 5, you can always follow time zones and basically choose your write region programmatically using our ARM APIs and basically choose the write region dynamically based off of the time of day. Now, replication is incomplete without consistency. If you do not have a tunable consistency model, then all you have is geo-replication for disaster recovery. You have not solved the low latency problem because you basically cannot guarantee predictability of these read requests. So to explain this, what I have here in this diagram is a partition set. You know that a container is composed of many partition sets. And each of those partition sets is actually not even a single machine. It's 4 replicas within each database region. So here I'm going to just take out one such partition set out of the container. I'm going to zoom in, and I have deployed this container in 3 separate Azure regions: West US, East US, and North Europe. When a write comes in, it's going to go into the write region. It's going to go to the leader replica. It's going to synchronously replicate to a quorum of replicas within that write region, and then it's going to acknowledge. And this is all going to happen in 15 milliseconds or less. Now, from here, it's going to asynchronously replicate to these 2 other regions, East US and North Europe, because when you're talking about large geographic distances, you're now talking about much higher latencies. So, let's use an example here. In this setup, what I'm going to do is I'm going to start with a single record that's been replicated to all of these different regions, and the value within record is 5. And to illustrate consistency, here's what we're going to do. We're going to update that value from 5 to 6. It's going to do the synchronous local quorum commit. It's going to acknowledge, and now it's going to replicate to all of the other regions. Let's say I have observers in some of these other regions, and at the same time, I'm going to have a failure. I'm going to actually have a network partition. Let's say a major earthquake has just happened, and network connectivity to one of the data centers has been lost. Well, if you literally cannot communicate between two replicas, that means they cannot have a consistent view of the world because they can't communicate with each other, right? But then what is the behavior of the system? If it still has active read requests coming in, does the database actually send you whatever copy it has, even though it might not be consistent with the rest of the world? And this is what people refer to as availability with regards to CAP theorem. Or does it actually go, hey, because I cannot guarantee that all of the other replicas are seeing what I'm seeing, I cannot guarantee a consistent view of the world, then what's going to happen is I'm going to sacrifice availability. Most people actually know this as CAP theorem. Basically, Brewer's CAP theorem says it's actually the academic way of codifying given consistency, availability, and partition tolerance, and it's impossible for a database system to actually guarantee all three. This is just simple physics. But the thing about CAP theorem is it doesn't go far enough, because it only talks about the unhappy path, right? What happens in this edge case when a data center loses communication? But what about the common case? What happens during just normal operation, which is going to be the vast majority of time, right? Basically, replication and replicating this data, well, it can take hundreds of milliseconds because the other data center, the other replicas might be halfway around the world. And so if I now have an active workload and asking like, hey, I want to serve a read request, what is the value that's presented? Is it actually going to get a consistent view with the readers observing from other regions? Basically, should this, because I've now updated 5 to 6, 2 of my regions have now reflected the 5 to 6 change. The third one's still lagging behind at value 5. What should it see? So the first thing you can do is you can think of it as, well, maybe I'll just prioritize latency. I have something that's very latency sensitive. Whatever copy of data you have, just serve it to me. It's okay if it's stale. That's prioritizing performance. Performance can actually also be measured in terms of throughput. And when you think about throughput, because we do a quorum commit on the write path, 3 or 4 replicas will say, hey, I have that copy of data. And that means if I want to give you things like strong consistency, I now actually need to do things like a quorum read. So rather than read a single replica, in which case that one replica might have a stale copy of data, I now want to read it from a quorum of replicas, so that way I can guarantee consistency. Basically, there's also this trade-off between throughput versus consistency. And the other thing you can do is you can prioritize consistency over this performance, right? You can say, you know what? A database replica says, I am seeing active write workload happening in all of these Azure regions. I know that's happening. I know I don't have a consistent view of the world. So hold on, let me catch up and then serve you your data. And now you're paying a performance penalty for that consistency. This is codified in the academic world as PASELC. There's a lot of literature on this. Actually, there's a very famous article published by, I think, Daniel Abadi as part of Yale University. If you're interested in this topic, actually do give that paper a read. But what this translates to you as an application developer and in terms of kind of more of a pragmatic view of the world, basically you now have this strong trade-off between strong consistency and high latency versus eventual consistency and low latency. A lot of databases will force you into these extremes, but the thing is that the world doesn't have to be black and white. This is where Cosmos DB is really showing something very novel here. What we do is we actually give you 5 tunable consistency models. They're overridable on a per request basis, and this will then give you very, very clear trade-offs for consistency versus latency, availability, and throughput. This is configurable easily through a single click of a button on the Azure portal. You just click on the default consistency, you choose one of the 5 consistency models, and that's about it. You don't have to do any crazy quorum configuration, replica configuration, data center configuration. Screw all of that. Let's make this just a click of a button. Now, let's talk about each of the different consistency models because I know that I realize this is kind of like a new novel space. Basically, here I have the 5 consistency models: strong, bounded, staleness, session, consistent prefix, and eventual, labeled from left to right. And basically, if you go from left to right, basically we're going to go from strong consistency to eventual, and this means lower latency, higher availability, and better read scalability as you move to the right. So let's kind of demystify this and talk about some of the actual real-world scenarios. For strong consistency, what we're really guaranteeing is this concept of linearizability, meaning when a write operation is complete, that write is made visible to all subsequent requests. This is useful for maybe in context, let's say, an order processing system. Let's say I didn't implement my order processing system in like an event sourcing model, but rather what I'm doing is I'm making a query to the database and looking for any records, orders that aren't processed, and then I'm going to take those orders, and then I'm going to process them for payment. Now, if I process an order for payment, I update that record, and then do a follow-up read. What you don't want happening is a database serving a stale read. If you see the same record now come back, and it's an order you already processed, but it says unprocessed, you charge it for payment again, and further down the line, you're going to have a customer calling you up going, "Hey man, why did you charge my credit card like 5 times for the same order? Like, I don't get it," right? So in this scenario, you want strong consistency. However, if I have, let's say, a social media application, I'm using something like Facebook. In that case, you know what? There's a billion other users out there. I don't want to pay the performance penalty for all billion other users, clicking like button. Instead, I want this page to load as snappy, as fast as possible. And so rather than giving a strongly consistent read, I want to prioritize performance. And so these give you kind of the extremes. And now let's talk about some of the click stops in between. A little bit stronger than eventual is consistent prefix. Let's talk about a messaging application. For a messaging application, what I might do is I have a conversation group chat with my friends Heather, Jacob, and Nick. And what we're doing is we're discussing dinner plans. And I'm saying, "Hey man, like, what time do you want to do dinner?" Someone replies, 7 p.m. And I say, "Oh, I can't do 7 p.m. I'm actually busy at 7. Someone says, "How about 8 p.m.? And now someone else says, "Oh, that works great. I'll see you there." Now, the thing is that if you have eventually consistent system, that means these write requests, these messages are being replicated in the order that we receive, as soon as we receive them. That means network packets can actually travel faster than other network packets, and these actually might arrive out of order. And if you see this out of order on a subsequent read, some people say 8 p.m., no, that doesn't work. 7 p.m., other people see 7 p.m., no, that doesn't work. 8 p.m., well, pretty soon half the group is going to be wondering, "Hey, what happened? Like, I arrived, and you guys are done with dinner." Meanwhile, the other half is going, "Hey, where were you? No, like, we've been here, we've been eating dinner. Why are you like an hour late?" And so consistent prefix is the idea that rather than replicating write requests as we see them, what we're going to do is we're going to replicate them in order. Basically, we have a log structure database, and we're going to replicate based off of operations being appended to the log. And what that means is you'll never see these out-of-order operations. You'll also never see gaps in time. So if you see record number 3, you'll see 2 and 1. You won't see 2 missing. You won't see 3 and then 1. We can strengthen this further with session consistency. The concept of session consistency is basically maintaining strong consistency within the scope of the session and consistent prefix outside of the scope of that session. Basically, I can read my own writes. And social media is actually a very good example of that. Going back to the Facebook example, session consistency is probably actually the right model to choose here, because while I don't want to pay the performance penalty for everyone else's comments, everyone else's wall post, I do want to actually see my own. If I post a comment and I hit the refresh button and I see my comment disappeared, I'm going to be confused, right? And so what I'm going to do is I'm going to go and just post a comment again. and I refresh the page, it disappears again because I got a stale read, and now I'm getting frustrated, so I post it a third time, and I say, fine, if this time it doesn't take it, I'm not going to post it again. Meanwhile, my friend Heather is watching Facebook, and Andrew just keeps posting the same comment over and over again, and she's just laughing at me, going like, what is this guy doing? Like, is is something like wrong with you? Like, why are you saying the same thing over and over again? And so what I want to be able to do is I want to be able to read my own writes with a strong consistency. Well, then session consistency is the right model for you. We also have one more way of defining a consistency model, and that is bounded staleness. In the bounded staleness model, what we're doing is we're actually defining a window of time as well as a window of operations. And this is a moving window. Over time, this window keeps moving. And basically, within this window, we only guarantee consistent prefix. Outside of this window, we actually guarantee strong consistency. This basically now gives you a very formal way of guaranteeing how eventual is eventual consistency. Bounded staleness is very easy to configure. When you click on it, you just define the number of operations as well as the amount of time. And what we'll do is we'll make sure that we stick to these bounds. If we ever hit one of these bounds, we'll prioritize replication over other processes. We might even throttle the write path to force replicas to catch up. For session consistency is maintained through the use of a session token. Every time you perform a write request, we'll give you a session token. Every time you do a read request, you can actually apply the same session token to pin it to that session. By default, we actually cache all of these session tokens on the client SDK. But if you have, let's say, a fleet, like hundreds of stateless application instances, you want to maintain the session, what you can do is upon a database write, your application actually passes back to the end user, let's say a browser cookie, storing the session token, and then when he makes follow-up requests, he passes that session token back in, goes to another application instance, and that way you guarantee session. You can also relax consistency on a per request basis. You do so by simply overriding the request operations for your database requests. And this basically concludes our session. We've basically talked about the business and technical challenges with one of our real-world scenarios, with one of our real-world customers. We went over our real-time personalization architecture, our reference architecture. We've done a deep dive on Azure Cosmos DB. And if you'd like to learn more, do visit our website. Follow us on Twitter. We regularly post updates there. Or if you have technical questions, we also monitor our Stack Overflow tag very closely. Thank you very much.